Welcome back to QHSE Talks.
Thank you. It's great to be back.
So imagine a heavy steel cylinder about the size of a person just sitting quietly in a warehouse.
Right, just blending into the background.
Exactly. I mean, it looks like a stationary piece of metal. It seems utterly harmless.
But it really isn't.
No, not at all, because in a fraction of a second, say, a forklift backs into it. Its brass valve snaps off, and it instantly transforms into an unguided rocket.
Yeah, literally punching a hole straight through a concrete block wall and, flying across the yard.
It's terrifying to even picture.
It is the ultimate hidden kinetic threat.
Right.
I mean, we're used to hazards we can actually see.
Right, like a spinning saw blade.
Exactly. Or an open trench or a suspended load. Those are tangible things.
You can walk around them?
Right. But the energy locked inside a pressure vessel gives absolutely no visual warning of its presence. Or its volatility, really, until the exact millisecond that containment fails. You are dealing with immense forces, sometimes thousands of pounds per square inch, just waiting for an escape route.
And providing you with the roadmap to understand, manage, and really respect those forces is exactly our mission today.
Absolutely.
We're speaking directly to you, the listener. We know that many of you might be preparing for the ASP certification exam.
Specifically targeting Domain 2, Topic 8, Part L.
Right. Or, maybe you're not taking the exam right now and you are just looking to master the safety fundamentals of compressed gases and pressure vessels for your facility.
Which is just as important.
Either way, you are in the right place, because passing that exam or protecting your workers requires a lot more than just memorizing OSHA standards.
Yeah, it requires a fundamental grasp of the physical universe.
Which is why we have assembled a massive stack of sources to decode this topic for our QHSE Talks today.
We've got a lot to get through.
We really do. We're integrating the BCSP examination blueprints, comprehensive study guides, the Bowen EHS practice problem sets.
And don't forget, the CCPS 20 elements of risk-based process safety.
Oh, yeah, and those dense engineering handbooks like Brower Safety and Health for Engineers.
Right. We are going to break down the physics, the hazards, the engineered controls, and the management systems.
Because if you don't understand the why behind the pressure, the safety rules just look like, arbitrary text on a page.
Exactly. They just become a checklist instead of a lifesaver.
Okay, let's unpack this. Where do we even begin with something as fundamental as understanding what a gas actually is?
Well, I think we have to start at the absolute baseline.
It feels like we need to zoom all the way down to the molecular level to really appreciate the hazard.
What's fascinating here is that the behavioral properties of a gas dictate every single safety protocol we have.
Okay, so how do the sources define it?
Our sources define the physical state of a gas by contrasting it with liquids and solids.
Right, the states of matter.
Yeah. So in a solid, molecules are locked tightly together in a lattice. They vibrate, but they don't migrate.
They stay put.
Right. Then in a liquid, the cohesive forces between the molecules are strong enough to give the liquid a definite volume.
But not a fixed shape, right?
Exactly. They slide past each other, but they generally stay together in a pool at the bottom of a container due to gravity.
Okay, that makes sense. But a gas plays by an entirely different set of rules.
Completely different.
The defining characteristics laid out in the texts are low density, low viscosity, high elasticity, and extreme expansiveness.
Yeah, at the molecular level, the cohesive forces between gas molecules are almost non-existent.
So they just bounce around everywhere.
Pretty much. They are in a constant state of chaotic, random motion. They travel in straight lines until they collide with each other or, with the walls of whatever's holding them.
That sounds like a lot of energy.
It is. Because they lack those cohesive bonds, gases will expand infinitely to fill whatever volume you give them.
Wow. Infinitely.
Yeah. If you open a cylinder of gas in a room, those molecules will eventually distribute themselves throughout the entire room.
So when we compress a gas, we are essentially fighting against its fundamental nature.
That's a perfect way to put it. You're fighting nature.
We are forcing billions of wildly moving molecules into an artificially tiny space.
Right, a steel cage.
And every time one of those molecules ricochets off the inside of the steel cylinder, it exerts a tiny amount of force.
Exactly.
Multiply that by trillions of molecules, and you get pressure.
Precisely. You are storing up a massive reservoir of kinetic energy.
And I'm guessing there's a law that governs all this.
Oh, definitely. The rules governing how that energy behaves are dictated by the Boyle-Charles law.
Oh, right. Often referred to in safety exams as the combined gas law.
Yeah, that's the one. This is the absolute foundation of thermodynamics for a safety professional.
The classic equation. P1 times V1 over T1 equals P2 times V2 over T2.
Pressure, volume, and temperature.
They are inextricably linked, aren't they?
They are completely interdependent. What this law tells us is that if you alter one of those variables, the others, they absolutely must compensate.
Okay, so give me an example of how that works in the real world.
Well, if you hold the volume
Yeah.
constant, meaning you have a rigid steel cylinder that cannot physically expand.
Right, a normal gas tank.
Yeah. And you increase the temperature, the pressure absolutely must increase.
Because the heat makes the molecules move faster.
Exactly. The heat energy transfers to the gas molecules. They move faster. They hit the walls of the container with greater velocity and higher frequency.
And that registers on a gauge as an increase in pressure.
You got it.
Let's walk through the specific example from the source text, because I think this really grounds it in reality.
Yeah, it's very helpful, especially for exam prep where they throw these word problems at you.
Right. The text gives a scenario of a 208.197 liter container stored in an unventilated warehouse.
It's a perfect practical application.
Yeah.
Let's run the numbers exactly as a safety professional would need to on the job.
Okay, I'm ready.
We start with the initial state. The container is sitting at 14.7 psi, which is standard atmospheric pressure at sea level.
Okay, and what's the temperature?
The ambient temperature is 299.67 Kelvin.
Which translates to roughly 80 degrees Fahrenheit, right?
Correct. A totally normal, warm summer day in a warehouse.
Sounds nice enough.
But it's an unventilated space. So the height of the afternoon hits, the sun beats down on the metal roof.
And it gets hot.
Very hot. The temperature in that specific storage location increases to 312.44 Kelvin.
Or about 102 degrees Fahrenheit.
Exactly. So what happens to the pressure inside that sealed, rigid container?
Well, because the volume of that 208-liter container is fixed, the math is straightforward. The temperature went up, so the pressure must go up proportionally.
Exactly right.
You calculate it out, and the pressure increases to 15.33 psi.
Yep, that's the number.
Now, I can hear someone studying for the ASP looking at that and thinking, well, 14.7 to 15.33, that's a difference of less than 1 CSI?
It sounds negligible.
Yeah, that doesn't sound catastrophic at all.
It doesn't sound like much until you break down what PSI actually means, pounds per square inch.
Oh, right, every single square inch.
Yeah. Yes. You have to multiply that fraction of a pound across every single square inch of the internal surface area of that entire 208-liter container.
That adds up fast.
Fast and heavy. We are talking about hundreds, potentially thousands of pounds of new outward force pushing against the steel, the welds, and the valve threads.
Wow.
If that container was a low-pressure vessel, only rated for atmospheric pressure, and lacked a sufficient safety factor, that temperature spike just pushed it past its yield strength.
And that's just a regular warehouse in the summer.
Exactly.
Imagine a cylinder sitting in the back of a black pickup truck in direct sunlight, or, stationed too close to a radiant heat source like a furnace or a hot work operation.
The temperature spike would be immense.
And therefore the pressure spike would be immense, which perfectly explains why the engineering handbooks are so dogmatic about never exposing pressurized containers to direct heat sources.
The physics simply won't allow it to be safe. It is a mathematical certainty that the pressure will rise.
Here's where it gets really interesting, though, especially when we were calculating these gas laws for the exam.
Oh, you mean the STP variations?
Yes. We constantly run into the acronym STP standard, temperature, and pressure. But the sources point out a detail that I know trips up a lot of professionals.
It absolutely does.
Depending on the specific hat you are wearing as a safety professional, STP actually changes.
This is a vital distinction for the listener, and frankly, it is a classic trap on the ASP certification exam.
Good to know.
You absolutely must know which standard to apply based on the context of the question, or your calculation will be fundamentally wrong.
I've always found it a bit frustrating. You'd think standard would just mean one universal standard.
You would think so, yeah.
But the baselines shift. Let's break this down. Let's start with industrial hygiene.
Okay. If you were doing an industrial hygiene calculation, for instance, you are determining the parts per million concentration of a toxic solvent vapor. A worker is breathing. FTP is defined as 25 degrees Celsius and 1 atmosphere of pressure.
Which is roughly 77 degrees Fahrenheit. That makes perfect logical sense.
Right, because of the human element.
Exactly. Industrial hygiene is about human exposure, and 25 Celsius is a standard, comfortable room temperature where people are typically working, breathing, and metabolizing.
Exactly. The volume of a gas and therefore its concentration in the air depends on the temperature. So IH uses a temperature relevant to human biology.
Okay, but what if you shift gears?
Right. If you are doing ventilation calculations.
Like designing the ductwork for a facility.
Yes. Or calculating cubic feet per minute of airflow, or figuring out the density of air for a fan motor sizing. In those cases, STP shifts slightly.
What does it shift to?
For ventilation, it is defined as 70 degrees Fahrenheit and 1 atmosphere.
Okay, so slightly cooler.
Yeah, slightly cooler.
And then there's the physical sciences definition, which is entirely different.
Very different if you were doing pure chemistry or physics calculations.
Like calculating the exact molar volume of an ideal gas.
Right, or balancing a stoichiometric equation for a combustion reaction. In those cases, the physical sciences STP is 0 degrees Celsius and 1 atmosphere.
Wait, 0 degrees, that's freezing point.
Right. It's an absolute baseline for laboratory physics, entirely unconcerned with human comfort.
That is wild.
So if an exam question asks you to calculate something at STP, your very first analytical step has to be identifying the context.
You have to figure out who you are in the scenario.
Precisely. Are you acting as an industrial hygienist assessing a chemical exposure? Are you acting as a ventilation engineer? Or are you acting as a chemist?
Because using 0 degrees Celsius in your ideal gas law equation, when you should be using 25 degrees Celsius, will drastically change the volume and concentration numbers in your math.
Oh, drastically. It's not a minor rounding error.
Right. It will point you to the wrong multiple choice answer entirely.
And beyond the exam, in the real world, it represents a fundamental misunderstanding of the application.
What's the real-world consequence?
Well, miscalculating a toxic exposure concentration because you used a freezing point standard could lead you to approve a confined space entry that is actually lethal.
Oh, wow. Okay, that is terrifying.
It is. The stakes are incredibly high.
So we've established that this immense pressure is a kinetic threat just waiting to escape, driven by temperature and thermodynamics.
Yep.
So if we know that the gas is desperately trying to expand, what happens when that energy is released uncontrollably?
That's where things get violent.
Let's dive into the arsenal of hazards we are dealing with when containment fails.
The hazards of compressed gases are incredibly complex because they combine the mechanical violence of an explosive blast with the toxicological, corrosive, or flammability threats of a hazardous chemical.
It's a 2-for-1 deal of danger.
Exactly. You are dealing with multiple hazard vectors simultaneously.
Let's start with the sheer physical violence. We mentioned it in the introduction. The missile effect.
Yeah, that's a big one.
The sources spend a lot of time on this. We have to visualize the anatomy of a standard high-pressure cylinder.
Okay, picture it.
It's a heavy, thick-walled steel tube engineered to hold incredible force. But at the very top, tapering down to a narrow opening, is a brass valve assembly.
Right.
That brass valve is the structural bottleneck.
It is the weakest point of the entire containment system, holding back, in many industrial applications, over 2,000 to 3,000 pounds of pressure per square inch.
So if an unrestrained cylinder is knocked over and the neck hits the edge of a steel table, shearing that brass valve cleanly off, what is the physical mechanism of what happens next?
You have instantly created a jet engine.
Just like that.
Just like that. The rapid, uncontrolled release of 2,000 psi of gas through a hole the size of a quarter generates massive instantaneous thrust.
Newton's third law of motion, right?
Exactly. For every action, there is an equal and opposite reaction. The gas violently blasts out in one direction, and the heavy steel cylinder is propelled in the exact opposite direction.
The text notes that because of the mass of the cylinder, often over 100 pounds of solid steel, and the velocity it attains from that thrust, the momentum is just catastrophic.
It will easily tear through structural steel, brick walls, vehicles, and human bodies.
It's a wrecking ball.
And because a cylinder is not aerodynamically stabilized with fins like a real rocket, its flight path is entirely unpredictable.
It doesn't shoot straight.
No, it tumbles, it ricochets off the floor, bounces off the ceiling, and destroys everything in its path until the internal pressure finally equalizes with the atmosphere.
It is effectively an unguided torpedo.
It really is.
And it's not just the cylinders themselves that become projectiles.
Look,
the sources heavily emphasize the danger of whipping lines, which is a hazard that operators face much more frequently.
Whipping lines occur when the distribution system fails.
Right, like the hoses.
Yeah. Manufacturing facilities use vast networks of flexible hoses to distribute compressed air, hydraulics, or process gases to tools and machinery.
And the fluid dynamics here are terrifying.
Very.
If a high-pressure flexible line severs or a fitting blows off at the end of a run, the sudden release of pressure causes the hose to act like an unrestrained fire hose.
Because the gas is escaping, pushing back against the hose, but the hose is flexible, so it just thrashes.
Exactly. The kinetic energy transfer causes the hose to violently whip back and forth in a chaotic radius.
It's so dangerous.
A heavy-duty industrial hose flailing around at near supersonic speeds can shatter bones, cause severe blunt force trauma, or, strike someone in the head with lethal force.
And the human instinct, if you see a hose suddenly detach and start thrashing, is to reach out and try to grab it to stop it.
Which is the worst thing you can do.
Absolutely the worst. You cannot physically overpower a whipping high-pressure line.
The forces are just too high.
The energy output far exceeds human grip strength.
Yeah.
You will only pull yourself into the impact zone.
There is another physical hazard detailed in the text that is far more insidious and honestly a bit gruesome. Injection and internal injuries.
Okay.
It's a classic, tragically common workplace incident, usually involving compressed air.
People naturally assume compressed air is safe because they breathe air every day. They don't respect the mechanical force it carries.
It's incredibly common on a shop floor. A worker finishes a shift covered in sawdust or metal shavings, and they grab a compressed air hose to blow the dust off their clothes or clean debris off their skin.
Which is a huge violation.
Right. The engineering guidelines state a strict non-negotiable rule. Compressed air nozzles used for cleaning must be restricted to less than 30 psi.
We need to explain the mechanical reason for that specific threshold.
Let's do it. Why 30 psi?
The 30 psi limit exists because of the tensile strength of human skin.
Okay.
Above 30 psi, the pressure of the airstream is literally stronger than the structural integrity of the epidermis.
Wow.
If you have a standard nozzle-blowing, unregulated high-pressure air, say 90 or 100 psi, and you pass it over your hand, the air can actually penetrate the pores of the skin.
Just push right through.
Yes, or it can force its way into an existing microcut or scratch.
And once that pressurized air breaches the skin barrier, it doesn't just harmlessly dissipate, does it?
No, it expands rapidly inside the body. It forces its way into the subcutaneous tissues, creating massive internal trauma.
That sounds horrific.
It can separate the skin layer from the underlying fascia and muscle, essentially inflating the tissue.
Oh, man.
Even more terrifying, if the pressurized air enters the bloodstream through a cut, it creates an air embolism.
A physical bubble of air trapped in the vascular system.
And that bubble travels with the blood flow. If it reaches the heart, it can cause cardiac arrest by vapor locking the pumping mechanism.
It just stops the heart.
Right. If it travels to the brain, it blocks a blood vessel and causes a massive stroke. It is a highly lethal event triggered by something as seemingly innocent as dusting off a shirt.
The texts also warn about air entering bodily orifices. If someone playfully points an air hose at someone's face, and air enters the mouth.
The sudden expansion of gas can instantly rupture the lungs or the stomach lining.
Which is why the safety professional must ensure that any air used for cleaning is heavily regulated down to that safe sub 30 psi limit.
Exactly.
This is typically achieved through engineered safety nozzles, right?
Yes. These specialized nozzles have relief ports built into the sides. So if the tip is dead-ended against a surface like a worker's hand, the air exhausts out the sides, preventing the static pressure from ever building up enough to breach the skin.
Okay, so those are the physical, kinetic hazards of the pressure itself. But the sources also require us to master the chemical properties of the gases.
Because what is inside that cylinder dictates the secondary disaster once containment fails.
The ASP blueprint demands a deep understanding of several key chemical parameters. You can't just manage the pressure, you have to manage the substance.
Right. The most fundamental distinction is understanding flammable versus oxidizing gases.
It's a common misconception on the shop floor that oxygen is highly flammable. Workers think if you strike a match near an oxygen tank, the tank itself explodes in a fireball.
That's a very common myth.
But for the exer and for process safety, we have to be chemically precise.
Exactly. A flammable gas like acetylene, hydrogen, or propane is the fuel. It is the hydrocarbon or chemical structure that undergoes combustion. An oxidizing gas, like pure oxygen, nitrous oxide, or chlorine, does not burn on its own.
So oxygen isn't the fuel, it's the accelerant.
Oxygen is the chemical agent that steals electrons during the chemical reaction of a fire. It allows the fuel to burn.
Okay, I see.
If you release a massive cloud of pure oxygen into a completely sterile, empty room, it will not ignite, no matter how many sparks you introduce.
Because there's no fuel.
Right.
Yeah.
But if there's even a tiny spark and any combustible material present.
And in a pure oxygen environment, materials we normally consider non-flammable suddenly become highly volatile.
Exactly. Combustion happens instantly.
We're talking about things like heavy machine grease, standard cotton clothing, or even certain metals burning furiously.
Yes, pure oxygen lowers the ignition temperature and massively accelerates the combustion rate. So while it doesn't burn itself, it turns everything else around it into a potential bomb.
We will definitely get into how strict the storage rules are for oxidizers a bit later because the regulations are intense.
Very intense.
But beyond flammability, the texts require us to understand specific gravity and vapor density.
These are fundamental concepts for emergency response and ventilation design.
Let's break those down.
Specific gravity compares the density of a liquid or solid to the density of water. Water is the baseline, given a value of 1.
So if a chemical has a specific gravity of 0.8, it's lighter than water and will float.
Right.
If it's 1.2, it's heavier and will sink.
Exactly. Vapor density uses the same concept, but it compares the density of a gas or vapor to the density of ambient air. Air is the baseline of 1.
So why does a safety professional need to have this memorized?
Because it dictates where the hazard goes when it leaks.
Tracking the gas.
Right. If you have a leaking gas with a vapor density significantly greater than one like propane or chlorine, it is physically heavier than the surrounding air.
So it falls.
It will not dissipate upwards into the atmosphere. The fluid dynamics of the gas will cause it to sink.
Where does it go?
It will pool in the lowest topographical points of your facility. It will flow like an invisible waterfall down into drains, trenches, confined spaces, and elevator shafts.
Which creates a terrifying scenario. A worker walking down the stairs into a basement or stepping into a utility trench might walk right into an invisible lake of heavy, toxic, or flammable gas.
Exactly.
The air at head height might be perfectly clean, but at knee height, they are wading through an explosive mixture.
And that leads directly to the last vital chemical parameters, the LEL and UAL, or the lower and upper explosive limits.
I remember studying these.
These limits define the precise concentration range in which a vapor-air mixture will actually ignite and sustain a flame.
I always like to break this down mechanically. The LEL is the lower limit. If the concentration of flammable gas is below the LEL, we say the mixture is too lean.
Yes, too lean.
What does that actually mean at a chemical level?
It means there simply aren't enough fuel molecules dispersed in the air to sustain a chain reaction.
Even with a spark.
Even if you introduce a spark, the few fuel molecules that ignite are too far apart from other fuel molecules to pass the heat energy along. The fire instantly starves.
And conversely, if the concentration is above the UEL, we say it's too rich.
In a too rich environment, the space is so saturated with fuel molecules that they've displaced the oxygen.
Oh, so it can't burn.
There isn't enough oxidizer available to bond with the abundant fuel. You can strike a spark in an environment that is 90% propane, and it won't explode because it lacks the oxygen to facilitate the chemical reaction.
The danger zone, the flammable range, is entirely between the LEL and the UEL.
Yes. And understanding where those limits sit for the specific gases in your facility dictates how you engineer your continuous gas monitoring alarms.
And how you design the dilution ventilation systems to keep concentrations safely below the LEL.
Exactly.
So we've established that this immense pressure is a kinetic threat, and the gases themselves are chemical landmines.
A deadly combination.
If we know a pressure spike is inevitable, whether from a temperature extreme, a blocked pipe, or a regulator failure, how do we engineer the system to give that energy an escape route on our terms, rather than waiting for a valve to snap off?
This brings us to the anatomy of protection. Whenever you have a pressurized system, the cardinal rule of process safety management is that you must design it with the absolute assumption that overpressurization will occur.
You can't just hope it doesn't.
You cannot rely on hope,
No.
and you cannot rely entirely on operational procedures.
Yeah.
You have to build in mechanical fail-safes.
The foundation of all of this engineering is knowing the MWP, correct?
Yes.
The maximum allowable working pressure.
The MWP is the absolute highest internal pressure that the weakest component in a closed system is safely engineered to handle under normal operating conditions and temperatures.
Everything has one.
Every single piece of equipment has one. From a massive 1,000-gallon volume tank acting as an air reservoir, down to the smallest quarter-inch pipe fitting or flange, they all have a designated MNWP.
And your safety relief systems must be meticulously calibrated based on that specific number.
They have to be.
You can't put a relief valve set to 150 psi on a vessel with an MWP of 100 psi, because the vessel will tear itself apart before the valve ever realizes there's a problem.
Exactly. The relief device must actuate before the pressure reaches the failure threshold of the vessel.
And there are a lot of devices to choose from.
The sources outline a whole catalog of different pressure relief devices, each engineered for very specific applications. They are not interchangeable.
Let's break down the mechanics of the different types. Because to the untrained eye, a valve is a valve.
But they behave very differently.
Right. There are fundamental operational differences between safety valves, relief valves, and safety relief valves.
They fall into distinct categories based on fluid dynamics and how they mechanically open.
Let's start with a relief valve.
A relief valve is primarily used for liquid systems, hydraulics, water lines.
Okay, liquids.
Liquids are non-compressible.
Yeah.
As pressure builds past the set point, a relief valve opens gradually, in direct proportion to the amount of overpressure.
So it's not a sudden blast.
Right. It bleeds off a little liquid to relieve the strain and opens wider if the pressure continues to climb.
Okay, gradual opening for liquids. What about gases?
For gases and vapors, you use a safety valve. Gases expand rapidly. If a gas system overpressurizes, you don't want a gradual bleed.
You need it out fast.
You want an immediate massive exhaust to save the vessel. A safety valve is engineered to pop fully open instantly the millisecond the set pressure is reached.
providing a full-bore pathway for the gas to escape.
Yes.
And a safety relief valve.
A safety relief valve is a hybrid device designed to function as either, depending on the application.
Oh, that's handy.
But the defining characteristic of all three of these valves is that they are mechanical devices utilizing springs and seats.
Right. There's a tightly coiled spring inside, holding a metal seat down against the pressure.
Exactly. The tension of the spring is calibrated to the MWP. When the internal pressure exerts more upward force than the spring's downward tension, the valve opens.
That makes perfect mechanical sense.
But crucially, once it vents enough gas or liquid and the internal pressure drops back down to a safe level, the spring regains the advantage and forces the valve to close and reseat itself.
So they are reusable. The system experiences an upset, the valve saves the day, reseats and operations can theoretically continue once the root cause of the pressure spike is addressed.
Ideally, yes. But mechanical devices have a flaw. They have moving parts.
And moving parts break.
Springs can lose tension over time due to metal fatigue. Valve seats can get corroded or encrusted with process fluids, causing them to stick shut.
So what's the backup?
This is why we also utilize non-mechanical sacrificial devices.
You're talking about frangible discs, which are more commonly known as rupture discs, and fusible plugs. I love the engineering elegance of these.
They are brilliant in their simplicity. A rupture disc is a very thin, meticulously engineered membrane of metal, graphite, or specialized polymer.
And no moving parts.
None. It has no moving parts. It is simply clamped into the piping system.
So how does it know when to pop?
The thickness and metallurgy of the disc are engineered to a molecular level so that it will physically burst at a very precise pressure point.
I always think of a rupture disc essentially like the mechanical version of an electrical fuse.
That's a great analogy.
If a circuit gets overloaded, the fuse burns itself out to break the circuit and save the expensive electronics. If a pressure vessel gets overloaded, the rupture disc destroys itself to save the main tank.
If we connect this to the bigger picture, in the hierarchy of controls, the rupture disc is the ultimate engineering control.
Because it's foolproof.
It relies on no human intervention, no electrical power source, and no moving parts that could succumb to friction or corrosion. The physics of the material simply fail at the exact moment they're designed to fail.
And then it's just open.
Once it bursts, it leaves a wide open, unobstructed path for the gas to escape. Of course, the downside is that the system must be completely shut down, depressurized, and the disc physically replaced before operations can resume.
Right. It's a one-time use item. And then there are fusible plugs, which operate on a completely different hazard trigger.
Fusible plugs are designed to combat temperature, not just internal pressure.
Where do we usually see those?
They're commonly found on acetylene cylinders or smaller compressed gas tanks. The plug is made of a eutectic metal alloy.
What does eutectic mean?
It's a specific blend of metals that is engineered to melt at a very precise, relatively low predetermined temperature, often around 212 degrees Fahrenheit.
So this is specifically designed for fire scenarios.
Exactly. If a cylinder is engulfed in a fire, The ambient heat might severely weaken the steel walls of the cylinder before the internal pressure rises enough to trigger a traditional pressure relief valve.
That's a race against time.
But the heat will quickly melt the fusible plug, creating a hole that allows the gas to safely vent and burn off.
Rather than remain trapped inside a weakening steel shell that will eventually rupture in a massive BLEV.
Right, a boiling liquid expanding vapor explosion.
But the text makes a massive point about what happens after these devices actuate. You've engineered a way for the pressure to escape, but you can't just let it blast out into the open air of a factory floor.
Not at all. Imagine a massive chemical plant. If a rupture disk bursts on a reactor vessel containing highly toxic hydrogen sulfide or extremely flammable ethylene gas,
You've got a huge problem.
you have successfully saved the vessel from exploding, but you have just initiated a catastrophic toxic release or vapor cloud explosion right in the middle of your workforce.
You solved the mechanical problem but created an environmental disaster.
Precisely. The engineering design must include routing the release.
Where does it go?
The discharge sides of these relief valves and rupture disks must be securely piped through heavy-duty discharge manifolds to a safe collection or destruction system.
What does that look like in practice?
If it's a highly flammable gas, the piping might route the release to a flare stack, a towering chimney with a continuous pilot light at the top.
So it just burns it off.
Yeah, it safely ignites and burns off the massive volume of gas high above the facility.
And if it's toxic?
If it's a toxic gas, the release might be routed through a chemical scrubber system that uses neutralizing liquids to strip the toxins out of the vapor before it hits the atmosphere.
That makes sense.
At the absolute minimum, for non-toxic, non-flammable gases, the vent pipes must discharge high above the roofline.
Just to get it away from people.
Utilizing dispersion models to ensure the gas plume never reaches a worker's breathing zone or an ignition source.
So engineering controls are the strongest defense. We've designed vessels to hold the pressure and fail-safes to vent it safely.
Right.
But at the end of the day, these systems still rely on human beings to interact with them, to transport them, and to use the gases for industrial processes.
Which is where things often go wrong.
Which brings us to the rules of engagement. How must safety professionals manage the day-to-day storage and handling of these cylinders?
This is where we transition from purely engineering controls to administrative controls and work practices.
The OSHA standards.
This is the realm of strict OSHA standards, specifically 1910 Subpart H for hazardous materials and industry guidelines from organizations like the Compressed Gas Association.
Let's start with the basics of storage. You see cylinders sitting around welding shops or construction sites all the time.
You do.
But there are very specific, physically mandated rules for how they must be staged. First and foremost, cylinders must always be stored upright. You can't just lay them down on the ground like a stack of logs.
There are profound physical and chemical reasons for that rule. Let's look at an acetylene cylinder.
Okay, let's look at acetylene.
Acetylene is highly unstable as a pure compressed gas. It can spontaneously decompose and explode at pressures above 15 psi.
Wait, if it explodes at 15 psi, how do they store it in a high-pressure cylinder?
Through a fascinating chemical trick. Inside an acetylene cylinder is a porous mass, like a highly engineered sponge that is completely saturated with liquid acetone.
Acetone, like nail polish remover.
Yes, acetone is a solvent. The acetylene gas is pumped in and it dissolves into the liquid acetone, much like carbon dioxide dissolves into water to make soda.
Oh, wow. I had no idea.
By dissolving it in the solvent, it becomes stable at high pressures.
Okay, so how does that relate to keeping the cylinder upright?
If you lay an acetylene cylinder flat on its side, the liquid acetone will pool near the valve.
And when you open it?
When the worker opens the valve to use the gas, they won't get gaseous acetylene. They will draw liquid acetone directly into the regulator and the hoses.
That sounds bad.
This will instantly destroy the regulator seals, clog the torch, and create a massive fire hazard.
That perfectly explains the why for acetylene. And I imagine keeping cylinders upright also minimizes the surface area exposed to physical damage.
Absolutely. A cylinder lying on the floor is a massive target for a forklift tire. Cylinders must be kept upright, and they must be secured, chained, strapped, or housed in a proper metal rack to prevent them from tipping over.
You can't just leave them standing on their own.
A freestanding cylinder is just waiting to be bumped, snapping that fragile valve off, and initiating the missile effect we discussed earlier.
And the caps.
Furthermore, the heavy metal valve protection caps must be firmly screwed on over the valve assembly whenever the cylinder is not actively connected to a regulator. That steel cap is the physical armor for the brass valve.
But the most famous storage rule, the one that every safety professional studying for the ASP has drilled into their brain, is the 20-foot rule regarding oxidizers and fuel gases.
It is a critical administrative control based purely on the chemistry of combustion.
As we established earlier, oxygen is the ultimate accelerant. It's the agent that makes everything else burn hot and faster.
Yes.
So why does it get put in solitary confinement away from everything else?
Because if you store your pure oxygen cylinders right next to your fuel gas cylinders, like propane, hydrogen, or acetylene, you have staged a perfect high-yield bomb.
A bomb just waiting to go off.
If a fire breaks out in the storage area or a piece of heavy equipment crashes into the rack and simultaneously breaches an oxygen cylinder and a fuel cylinder, the fuel and the massive supply of pure oxidizer will mix instantly in the atmosphere,
Creating a conflagration that no standard fire sprinkler system or fire extinguisher is going to be able to knock down.
It would be a catastrophic explosion. So OSHA mandates strict segregation. Oxygen cylinders in storage must be separated from fuel gas cylinders or any highly combustible materials by a minimum physical distance of 20 feet.
But 20 feet is a massive amount of real estate, especially in a crowded manufacturing facility or on a congested construction site. What if a facility literally doesn't have the square footage to separate them by 20 feet?
The standards provide an engineered alternative. You can store them closer together only if you separate them by building a non-combustible barrier,
Like a wall.
like a solid masonry or concrete block wall. That wall must be at least 5 feet high, and it must have a certified fire resistance rating of at least 1/2 hour.
So the wall acts as a physical shield. It prevents the gases from mingling in the event of a simultaneous leak.
And it provides a thermal barrier to delay heat transfer in the event of a fire, giving emergency responders a 30-minute window to intervene.
Exactly. Okay, so that covers storage, but what about when we actually put these gases to work?
That's where the operational rules come in.
Let's take the example of a welder setting up an oxyacetylene torch for hot work. The sources detail highly specific step-by-step procedures that must be followed before the torch is ever lit.
The handling rules are incredibly meticulous because that transition point moving the gas from high-pressure storage inside the cylinder to low-pressure usage in the hoses is highly vulnerable.
For example, before a worker even attaches the regulator to the cylinder valve, they are supposed to crack the valve.
Cracking the valve means turning the hand wheel to open the valve just a tiny fraction of an inch for a split second and then immediately slamming it closed again.
The purpose being to use a quick microscopic burst of the high-pressure gas to physically blow out any dust, dirt, or metal shavings that might have settled inside the valve outlet while it was in storage.
Correct. If you skip that step and attach the regulator directly, the moment you open the valve, that high-pressure stream will blast the dirt directly into the delicate internal diaphragms and seating mechanisms of the regulator,
Damaging the regulator.
This can cause the regulator to jam open, failing to reduce the pressure and blowing out the downstream hoses.
And when you do finally attach the regulator and open the cylinder valve to pressurize the system, the techs emphasize that you have to open it slowly. You can't just crank it open like a garden hose.
You must open it agonizingly slowly. This is due to a thermodynamic phenomena known as adiabatic compression.
Adiabatic compression.
And it is a massive hazard, particularly with pure oxygen systems.
Okay, here's where we really need to explain the why. What is the mechanism of adiabatic compression?
If a worker violently yanks the cylinder valve wide open instantly, a massive volume of high-pressure gas rushes into the small, confined space of the regulator body.
Just floods it.
It's essentially slamming into a dead end. The gas is compressed incredibly rapidly. When a gas is compressed, work is done on it, and that kinetic energy is converted into heat.
The same principle as a diesel engine. Compressing the air in the cylinder generates enough heat to ignite the fuel without a spark plug.
Exactly. But in a gas regulator, this compression happens so fast, in a fraction of a millisecond, that the heat has absolutely no time to dissipate into the surrounding brass body of the regulator.
Because it's adiabatic.
This is what adiabatic means, a process occurring without transfer of heat to the surroundings. The internal temperature of the gas inside the regulator can instantaneously spike to over 1,000 degrees Fahrenheit.
Wow. 1,000 degrees.
And if you are dealing with pure oxygen, and there is even a microscopic thumbprint of oil, a tiny speck of lint, or a hydrocarbon residue left inside that regulator,
I think I see where this is going.
that 1,000 degree spike provides the ignition temperature, the pure oxygen provides the accelerant, and the oil provides the fuel.
Boom.
The regulator literally detonates in the worker's hands. It is a violent, specialized explosion called an oxygen fire, and it happens purely because the valve was opened too quickly.
That is terrifying, and it perfectly illustrates why the rules exist. And speaking of the lines running from those regulators down to the cutting torch, there is a strict requirement for flashback preventers.
Yes. When a welder is using an oxy-fuel torch, they are mixing the fuel and the oxygen at the tip of the torch to create a controlled flame.
Right.
But if the torch tip gets clogged with molten slag, or if the gas pressures are improperly balanced, the flame can actually recede inside the torch tip and burn backward up the inside of the hoses.
Burning backwards inside the hose.
This is called a flashback.
And if that flame travels all the way back up the hose and reaches the cylinder, the entire rig explodes.
Which is why flashback preventers must be installed on the downstream side, right behind the torch handle.
What exactly is a flashback preventer?
A flashback preventer is an engineered safety device that usually contains a spring-loaded check valve to stop reverse gas flow.
Okay, so gas can only go one way.
And a sintered metal element, a porous piece of metal that acts as a flame arrestor.
How does that stop a fire?
If a flashback occurs, the flame tries to pass through the microscopic pores of the sintered metal, but the metal absorbs the heat so rapidly that it extinguishes the flame, stopping the fire dead in its tracks before it can reach the fuel supply.
We have spent a lot of time talking about keeping dangerous gases away from people and managing the gases we use as industrial tools.
Yes, we have.
But what about the gases we need people to breathe? This takes us to a critical area of safety engineering: life support, breathing air, and high-pressure environments.
This is perhaps the most profound application of pressurized gas because it involves actively sustaining human life in an environment that is, by definition, trying to kill the worker.
It's high stakes.
We are stepping into the realm of IDLH environments.
Immediately dangerous to life or health. These are the worst-case scenarios. A permit-required confined space filled with toxic solvent vapors, a trench completely depleted of oxygen, or the interior of a burning building.
In an IDLH environment, standard filtration masks, like an N95 or even a high-end chemical cartridge respirator, are entirely useless.
Because they just filter.
Right. You cannot filter air that doesn't have oxygen in it. The worker requires an independent, guaranteed supply of pure grade D breathing air.
This requires an SCBA, a self-contained breathing apparatus, where the worker wears a high-pressure cylinder on their back, exactly like a firefighter.
Or a supplied air respirator system, a SAR.
Where air is pumped down a long airline hose, but the worker still wears a small backup SCBA escape cylinder on their hip just in case the hose gets cut.
But the critical factor here is the source of that air. The air inside those high-pressure SCBA tanks, or the air being pumped down that airline, doesn't just magically appear.
It has to be compressed.
It has to be generated and pressurized by breathing air compressors. And the text makes it abundantly clear that these are not your standard industrial shop compressors used to run pneumatic nail guns.
Right. You can't just hook a breathing mask up to the greasy air compressor sitting in the corner of a mechanic's garage.
Absolutely not. The level of scrutiny placed on breathing air compressors is immense. When you compress atmospheric air, you are pulling in a massive volume of ambient air and squeezing it into a tiny space.
You're concentrating everything in that air.
That means you are also concentrating any airborne pollutants, moisture, dust, or chemical vapors that might be present near the compressor's intake valve.
So the compressors themselves have to be specialized, and the intake has to be strategically located away from exhaust vents.
Ideally for breathing air, you use an oilless compressor.
No oil at all.
A standard industrial compressor uses liquid oil to lubricate the rapidly moving metal pistons inside the compression chamber. But an oilless compressor relies on specialized, low-friction materials.
Like what?
Like Teflon rings and carbon graphite components, to reduce friction without the need for liquid lubrication. This physically guarantees that no oil mist or vapor can ever mix with the breathing air.
Furthermore, the compressed air must pass through extensive purification columns.
Yes, a series of desiccant dryers to strip out all the moisture, because moisture can freeze in the regulator valves.
And filters.
And activated carbon and catalyst beds to filter out particulates and neutralize chemical vapors.
But sometimes, heavy-duty industrial operations require massive, continuous volumes of breathing air for multiple workers over long shifts, and they have to use large, oil-lubricated compressors. And this introduces a profound, silent hazard.
If an oil-lubricated compressor is used to supply breathing air, OSHA mandates a strict non-negotiable requirement. The system must have an active inline carbon monoxide or CO alarm or a high-temperature alarm.
Where is carbon monoxide coming from? The compressor is just squeezing air, right?
The carbon monoxide comes from the lubricating oil itself.
Oh, wow.
If an oil-lubricated compressor overheats, which can happen due to a cooling fan failure, excessive mechanical friction, or just running it continuously on a hot day, the lubricating oil coating the inside of the compression cylinder begins to break down.
It burns.
As it overheats, it actually undergoes partial combustion. This thermal degradation of the oil creates carbon monoxide gas right inside the compression chamber.
Which is then pumped directly down the airline, straight into the worker's tightly sealed breathing mask.
Exactly. And because carbon monoxide is completely colorless, tasteless, and odorless, the worker has absolutely no sensory warning that they are breathing a lethal gas.
They don't know they're in danger.
They feel the cool airflow, they assume they are safe, but they're being poisoned.
The sources emphasize the biology of why CO is so incredibly lethal, and I think we need to break this down using an analogy because it's a vital concept for industrial hygiene.
The human body relies on hemoglobin, a protein in our red blood cells, to transport oxygen from the lungs to the brain and all the vital organs.
I always think of hemoglobin like a fleet of taxi cabs waiting in the lungs. When you take a breath of fresh air, oxygen molecules get into the cabs drive through the bloodstream and drop the oxygen off at the cells that need it.
That is a perfect mechanistic analogy. Now, the problem with carbon monoxide is its chemical affinity. CO molecules bond with hemoglobin approximately 200 to 300 times more easily and much more strongly than oxygen molecules do.
So using the taxi analogy, carbon monoxide is like a mob of highly aggressive people who rush into the lungs. Not only do they steal all the taxi cabs before the oxygen can get to them, but once they get inside, they essentially weld the doors shut.
Exactly. They refuse to let go. They form a compound called carboxyhemoglobin. Because the CO occupies the binding sites on the hemoglobin, it physically blocks oxygen from attaching.
Even if there is oxygen around.
So, a worker could be breathing a mixture that contains plenty of oxygen, but if there is CO present, the CO steals all the red blood cells. The blood circulating to the brain is completely devoid of oxygen.
So what does this all mean? The worker effectively suffocates from the inside out, suffering profound cellular hypoxia, all while breathing what they think is a steady supply of fresh air.
Which is why that continuous CO monitor on the compressor is not just a regulatory recommendation, it is a critical lifeline.
It's essential.
The sensor constantly samples the airstream. If the compressor runs hot and the oil starts generating even a trace amount of CO, the alarm sounds immediately,
alerting the safety watch.
Alerting them to switch the workers to their emergency escape cylinders and evacuate the IDLH space before the hypoxia sets in.
There is another fascinating detail in the sources regarding the biology of combustion and pressurized systems, and it relates to the engineering principle of substitution.
Yes, the aircraft tire example. It is a brilliant illustration of inherently safer design.
Let's talk about that.
Let's look at the physics of a massive commercial airliner landing. The plane weighs hundreds of thousands of pounds, and the tires hit the concrete runway at over 150 miles per hour.
The friction generated between the rubber and the runway in that split second is immense. It generates an incredible amount of heat very rapidly.
And those aircraft tires are highly pressurized, often over 200 psi, to carry that immense weight. Now, if those tires were inflated with standard compressed atmospheric air, we have a major problem. Standard air contains 21% oxygen.
The oxidizer.
Right. The intense heat from the landing skid transfers through the thick rubber of the tire. If the inside of the tire is filled with compressed air, the heat can actually cause the interior layers of the rubber tire to spontaneously ignite and burn from the inside out.
Fire inside the tire.
The oxygen in the compressed air acts as the oxidizer for the internal fire. The tire essentially becomes a localized bomb attached to the landing gear.
So how do aviation engineers solve it? They can't stop the plane from generating friction.
They solve it by substituting the gas. Instead of inflating the tires with compressed air, they fill them with pure pressurized nitrogen.
Because nitrogen is an inert gas.
Exactly. It does not support combustion. By filling the high-pressure tires with nitrogen, engineers have completely removed the oxidizer from the chemical equation inside the tire.
That's brilliant.
No matter how hot the friction makes the rubber on the outside, the tire cannot burn internally because there is absolutely no oxygen available to feed the combustion process.
It is a flawless application of removing one leg of the fire triangle through material substitution.
It really is.
That is such a clean, elegant engineering solution. But achieving this level of meticulous care across a massive industrial facility, from installing CO alarms on compressors to specifying nitrogen and high-friction tires, to meticulously calculating the MOWPs of pressure vessels requires more than just a good checklist or a single smart engineer.
It takes a lot more.
It requires a comprehensive, overarching organizational framework, which brings us to the systems level, the blueprint of process safety management.
You cannot manage the kinetic energy of a chemical plant solely by walking the floor and looking at pressure gauges. The sources heavily reference the CCPRS.
The Center for Chemical Process Safety?
Yes, and there are 20 elements of risk-based process safety. A safety professional is an architect of systems. You have to design a management framework that governs how the organization interacts with the hazards.
Let's unpack a few of the most critical elements as they directly relate to pressure vessels and compressed gases. The first one that jumps off the page is MOC, Management of Change.
Management of change is arguably the most vital, life-saving administrative control in any process facility.
How does it work?
The core concept is that anytime you modify a system that handles highly hazardous chemicals or high pressures, no matter how small or seemingly insignificant the change appears, it must go through a rigorous, formal engineering and safety review process before a single wrench is turned.
Even small things, like just replacing a short section of pipe or swapping out a broken valve.
Especially small things, because small things hide massive cascading failures. Let's look at a hypothetical case study. Let's say a maintenance worker on the night shift needs to replace a blown pressure relief valve on a process vessel.
Okay.
He goes to the storeroom, but they are out of the exact model specified on the blueprint. However, he finds another valve on the shelf that looks virtually identical and has the exact same thread size.
So he just swaps it out, thinking he fixed the problem and kept the line running.
Without an MOC review, he doesn't realize that the new valve has a spring calibrated for a much higher set pressure. The old valve was designed to pop at 100 psi. The new valve, despite looking the same, doesn't pop until 250 psi.
But the vessel itself has an MOWP of 150 psi.
Exactly. The worker has unwittingly removed the safety net. The next time the system overpressurizes, the new valve will hold tight and the vessel will rupture, causing a catastrophic explosion.
Just because of a swapped valve.
Or, what if they replace a section of heavy carbon steel piping with a polymer hose because it's easier to route around a corner, but the polymer has a much lower pressure rating?
Another disaster.
Or what if a process engineer decides to change the process fluid to something slightly more acidic to speed up production, but doesn't realize that the new acid will slowly eat away at the rubber O-ring seals of the existing pressure vessels?
An MOC process requires a multidisciplinary team engineers, safety professionals, operations managers to review the proposed change, analyze the new physics and chemistry, and update all the safety documentation to ensure that a simple maintenance swap doesn't inadvertently build a bomb.
And that leads directly into the next critical element: mechanical integrity and auditing.
Because even if you design it perfectly and you manage changes perfectly, the physical universe still dictates that metal degrades over time.
Entropy is undefeated. Pressure vessels are subjected to immense stress, thermal cycling, fatigue, and internal and external corrosion. The safety professional's role here is establishing the schedules and protocols for proactive, predictive inspection.
You can't just wait for a pipe to start leaking.
Mechanical integrity programs dictate regular, rigorous non-destructive testing, or NDT.
Like what?
This involves technicians using ultrasonic thickness gauges to measure the exact thickness of the steel walls of a tank to ensure corrosion hasn't thinned the metal below the safety threshold.
Oh, that's smart.
It involves taking X-ray radiography of pipeline welds to look for microscopic stress fractures. It involves hydrostatic pressure testing.
What's that?
Filling a pipeline with water and pressurizing it well past its normal operating pressure to physically prove it can still handle its MOWP without failing.
It also includes verifying the P&IDs, the process, and instrument diagrams.
Yes, ensuring that the engineering blueprints on paper actually match the physical reality of the plant out on the floor.
Because things drift.
If a P&ID diagram shows a pressure relief valve safely routing its discharge to a flare stack, but a mechanical integrity audit reveals that a contractor disconnected that pipe 5 years ago and now just vents directly into a closed room.
That audit just saved lives.
Exactly.
We also have to talk about the day-to-day administrative controls that govern how workers interact with the equipment.
This is where enforcing strict procedures like a LOTO lockout to gout becomes paramount. Before a maintenance worker touches a pressurized line, opens a vessel, or works on a pneumatic cylinder, that equipment must be completely isolated from its energy source.
It's not enough to just turn off the air compressor.
Not at all. You have to shut the supply valves, lock them closed with a physical padlock, and then, crucially for pneumatics, you must safely bleed off all the residual pressure trapped inside the lines.
Getting down to zero.
You have to achieve a state of zero mechanical energy. If you unbolt a flange while there's still 100 psi trapped behind it, that flange will blow off and take your head with it.
The text also mentions using physical barricades during specific high-risk operations, like inflating massive tires.
Inflating large, multi-piece rim truck tires or heavy equipment tires is notoriously dangerous. The rims are comprised of heavy steel rings that lock together.
Right.
If those rim components aren't seated perfectly during assembly, as the pressure builds inside the tire, the immense force can cause the steel rings to violently blow apart.
Sending heavy chunks of shrapnel flying across the shop.
With lethal force. So administrative controls dictate that these tires must be inflated inside a heavy steel barricade known as a tire cage.
And what does the cage do?
If the rim fails, the tire cage physically absorbs the kinetic energy of the flying metal components, keeping the mechanics safe.
When you look at all of this collectively, the MOCs, the ultrasonic integrity audits, the engineering of the relief valves, the tire cages, it really paints a vivid picture of the modern safety professional.
It's a big job.
You aren't just a rule enforcer walking around with a clipboard yelling at people to wear safety glasses. You are an architect of complex systems. The overarching philosophy is prevention through design. The goal is to design the hazard completely out of the process or heavily engineer the fail-safes long before the frontline worker ever interacts with the equipment.
This raises an important question, though, and it brings us to element 4 of the CCPS framework: workforce involvement.
The human element.
You can design the perfect system with flawless mechanical relief valves, meticulously updated PNIDs, and mathematically perfect MWPs. But how do you ensure the human workforce actually understands, respects, and follows these complex rules?
Right, because if the operators turning the valves and the maintenance techs turning the wrenches don't understand the fundamental physics of the Boyle-Charles law or the lethal biology of an oil-lubricated compressor generating carbon monoxide,
they will eventually bypass the engineering controls. They will view the rules as annoying bureaucratic hurdles rather than life-saving physics.
The safety management system must include rigorous, context-rich competency training. The operators and maintenance personnel must be intimately involved in process safety activities. They are the ones closest to the hazard every single day.
They need to understand the why.
When you explain the exact molecular reason for the 20-foot separation rule for oxygen, or the physiological mechanism of air embolisms driving the 30 PA cell for cleaning air, you aren't just giving orders, you're transferring knowledge.
When the workforce truly respects the hidden kinetic energy of pressure, the entire safety culture of the facility is elevated.
Okay, we have covered an immense amount of ground today, diving deep into the microscopic and the macroscopic forces at play. Let's briefly recap this journey. We started at the molecular level, unpacking the fundamental kinetic theory of gases and how the Boyle-Charles law dictates that temperature inevitably drives pressure.
We navigated the terrifying physical realities of containment failure. Newton's third law turning sheared cylinders into missiles, fluid dynamics creating bone-breaking whipping lines, and the silent, lethal mechanisms of injection injuries and air embolisms.
We also broke down the chemistry, detailing why heavy vapors pool in trenches, how LELs dictate ventilation, and why oxygen acts as a ferocious accelerant.
We explore the anatomy of protection, detailing how mechanical safety valves, frangible rupture discs, and eutectic fusible plugs act as the mechanical fuses of the industrial world, and why the release of that immense pressure must be safely routed to flares or scrubbers.
We broke down the strict administrative controls governing the shop floor, from the physics of keeping acetylene cylinders upright to prevent solvent damage, to the terrifying reality of adiabatic compression causing regulators to detonate.
To the absolute biological necessity of carbon monoxide alarms on breathing air compressors to prevent silent hypoxia.
And finally, we tied it all together with the blueprint of process safety management, how management of change prevents accidental bombs, and how mechanical integrity audits ensure these complex steel systems don't slowly degrade into disaster.
It's all connected.
For you, the listener, mastering this material isn't just about passing the ASP Domain 2 Topic 8 exam. I mean, yes, understanding STP variations and MWP calculations will definitely help you pass the exam. But more importantly, it's about altering how you view the physical world around you.
changing your perspective.
It's about having the fundamental knowledge to walk onto a job site, look at a simple, everyday compressed air hose or a storage rack of cylinders, and accurately calculate the real physical kinetic risks it poses.
That is the true lasting value of this knowledge. Every pressurized vessel around you, from the massive multi-story volume tanks at a petrochemical plant to the tiny aerosol cans sitting on your desk, is a trap storm.
A trap storm, I like that.
It is a highly concentrated package of potential energy held in check by metallurgy. The only thing standing between that potential energy and a kinetic disaster is human engineering and relentless administrative discipline. Tomorrow, when you walk through your facility, look at the pipes, look at the regulators, look at the cylinders, and ask yourself a simple question. If the engineering fails right now, where does the storm go?
That is a phenomenal thought to leave on. Thank you for joining us for this deep, detailed exploration into the world of pressure. We appreciate you taking the time to master these critical concepts with us. Stay safe out there, respect the invisible forces at work in your facilities, and we will see you next time on QHSE Talks.